Thank you very much, Claudia. And Oliver, I might actually need a Swiss Army knife to cut this presentation down to 2 minutes, because I think I only have 2 minutes left before you all go to lunch. But joking aside, I'm of course the only one between you and lunch, so I'm trying to speed up. Nevertheless, I would like to mention what could be a better fitting venue than the city of Jules Verne to talk about advances in technology and to explore the boundaries beyond the non-imaginary. So how does this work here? Well, the old-fashioned way. So, it's really important. If you look at this graph here, then you can see the leading cause of death in the Western world is and remains cardiovascular disease. So by the definition, what we are all doing here, or what you in the audience will be doing here, will be doing in the field of MR, is going to be hugely important. And in that context, we can take advantage of this wonderful non-invasive technology if we can better suppress motion, if we can make sharper images, if we can make better images, and this is exactly what this talk is about. So yes, it really matters what we are doing. Now, the first ever cardiac image I could get my hands on was given to me by this man here. This is actually Bill Edelstein, who invented spin warp, what we are referring to as phase encoding now. And on this very contraption, he acquired some of the very first images of the thorax. And you can see here this cross-section, axial image of the thorax. And what you can already see is motion artifacts in fold-over direction. And, he told me when he first saw that image, he thought, well, that must be related to the motion of the heart. He didn't give it any more thought, but this very first image, I think, very nicely exemplifies what we are still trying to get rid of so many, many years later. So why do we want to suppress motion? I already mentioned it. We ultimately want to improve diagnostic yield of this technology. And, how is this motion actually happening? Well, you see here on this slide in the background, you have two different motion components. I was speeding up the respiratory motion just for you, but you can see the heart is contracting, it's relaxing, it's bouncing up and down as a function of respiration. And so therefore, it's very hard to make sharp images during this moving heart. And here is a coronary artery. I drew it to scale, and you can see how it bounces around here in that circle, which is about 2 centimeters, constantly, vigorously. It doesn't stop. It's kind of unpredictable even. So therefore, we really need an interdisciplinary approach to tackle this hugely important problem. So if we were to collect data just across the cardiac cycle without interruption, then we would get to an image of a heart which is rather blurred, because we would be adding data that are non-consistent, basically as if you were taking a photo with an exposure time, shutter time that is too long, then the image of a moving object, of course, is going to be blurred. The solution to that is splitting up the data acquisition in equivalent pieces or segments that are relatively short, during which motion cannot have a major impact. And you can see here in this slide, I always do this at the same time point in the cardiac cycle, where I'm thinking that the heart always has the same shape. So I keep collecting segment by segment of the heart. Of course, you have to think case-based. I simplified this here, but you see the concept. By adding up these pieces, which were always acquired at the same time point, I can now get to a coherent image. And if I now add EKG gating to the image on your left, then you can see it already gets much sharper and certain details already can become visible. So in summary, how can we suppress cardiac motion? Well, the mainstay certainly is EKG gating or triggering. We segment case-based. We split up the acquisition in multiple acquisitions. We try to keep the acquisition intervals relatively short, and we also tend to acquire the images during a period of minimal myocardial motion if we are interested in anatomical details. However, this puts a major emphasis on the quality of how we get the EKG to trigger on. Moving on to the respiratory motion suppression, how can we get that done? You can see here, if you collect data during different respiratory phases and you're not careful, in how you're putting those together, you will have inconsistent data segments which are put together, which will lead to a heart that is actually also blurred or which has artifacts or gaps. How can we avoid that? Well, the most obvious approach is breath holding, which is easy to implement. It's clearly the preferred method for all the functional scans and late enhancement, perfusion, etc. It is non-vendor specific, which is of course an advantage, and the scanning times are by definition relatively short. However, the patient's ability to hold his or her breath then in turn governs the maximum spatial resolution you can obtain, so that's a disadvantage. Then oftentimes there is diaphragmatic drift during a breath hold. In between breath holds, there might be misregistration because the patient is not always able to hold his or her breath at the same level, and that leads to gaps or the so-called Venetian blind artifacts. And of course, in serial breath holds, you need a major operator and patient involvement. Is there somebody who would like to help me talk? Okay, how can we deal with that? Well, respiratory navigators have been introduced a couple of years ago by Dick Eamon and his team, which is basically a small MR image at the dome of the right hemidiaphragm. You look at this in real time, and in real time you make decisions about that position of that lung liver interface. So if this is, for instance, during end inspiration, you say that's not a good data point because I would like to collect the data during inspiration. So you tell the acquisition not to collect the data and remeasure those data again. So you keep doing that until you can piece together an image of the heart that always comes from the same respiratory position. Now, if you add this navigator technology to EKG gating, you can see again the image steadily keeps improving. So what are the advantages of navigators? Of course, the quality of the breath hold is no longer an issue. Image resolution can be improved. Operator involvement still is needed because you have to position that navigator. However, it offers you the opportunity, as I already mentioned, to go to high resolution, spend more time, acquire images in 3D, do signal averaging, etc., etc., and it has already been demonstrated to be effective in multi-center trials. However, the scan time is not only lengthy with this technology, it's also highly unpredictable because it depends on the respiratory pattern of the patient. These navigators are implemented in a vendor-specific fashion, which, however, becomes easier and easier to use. The results might be variable, and clearly there is operator dependency on how to position these navigators, etc., etc. This is actually a rather difficult task to do. And they cannot easily account for patient bulk motion, for instance. And one of the disadvantages might also be unfinished scans. So after having spent 10 minutes and you don't get the data because the patient drifts out of the window, this is actually not a very pleasant occasion. So in summary, how can we account for this respiratory motion? Well, we can do breath holding or we can use navigators to account for this. However, this requires patient and operator involvement, patient involvement mostly during the breath holds. What have we learned until now? Well, motion is a major challenge in cardiovascular MRI that can be dealt with, however. However, time inefficiency of the navigators, operator dependency, and ease of use still remain hurdles with these technologies. So just to exemplify these hurdles, ease of use and operator dependency, this is how we collect images. We have a scout scan, we plan a slice, we get to another visualization of this 2D heart, we plan an orthogonal section, on that we go again orthogonal, etc., etc. So this is relatively a lot of operator involvement, and you can easily imagine that not every operator will necessarily get to the same result. If you want to do this, for instance, for late enhancement using an inversion repulse during free breathing, then there is a lot of manual interaction needed. So everywhere where I drew a little hand, operator involvement is needed. So you need to put on the EKG electrodes, you have to futz around with timing parameters. You have to localize the slices. You have to position the navigator. You have to work on navigator gating parameters, etc., etc. So there is a lot to do for the operator. And this is part of the reason why this technology is mainly limited to academic centers. Just to jog your brain a little bit here, you know, if you count the number of mouse clicks that are needed for a brain scan versus a heart scan, I went down to the scanner and I had the technologist count mouse clicks. Okay, take a wild goose guess for the brain. Okay, here it is. It's about 12 mouse clicks. So why you need 12 mouse clicks for a simple brain beats me, I don't know. However, more importantly, if you count the mouse clicks for a cardiac exam, it's a whopping 350 mouse clicks, each of which could go wrong, right? That's why cardiac MR is so darn difficult. Second hurdle, time inefficiency. I drew a little matrix here. On the x-axis you have the cardiac contraction and relaxation. On the y-axis you have respiration. So you get to a matrix which you all understand, right? So what we now do is we wait until mid-diastole rolls around for imaging the anatomy, and we acquire these data during end expiration. So this is right here. However, if you think about this, how many times do these two instances coincide? It's very rare. So therefore, for most of the time, we are just twiddling our thumbs, doing nothing. And I looked at the AD converter of the pulse programming environment of the system. We clock in data during less than 2% of the time. I don't think this is a very modern approach, so Jules Verne would have a field trip in thinking about, you know, how to improve this situation. So what do we really want? We want something that is highly efficient, one mouse click. Some of you certainly know that. If you download a book on a certain vendor's web page, it's really one mouse click and you got this book, right? No credit card, nothing. It's just one mouse click and you get it done. Why can we not make cardiac MR the same way? Just one mouse click on a scout scan and you're done. You get basically out all the information you want from this one single marvelous scan. So we and other groups have been starting working on that, and we call this the free running framework. And this free running framework is basically built on three major pillars, one being the trajectory, in our case a radial 3D trajectory for collection of data in K-space. Secondly, we need to extract signals, motion signals, directly from K-space or from the acquired imaging data, and no longer from the EKG or from navigators. And finally, compressed sensing. Now, this young man had the idea to just do what I said we shouldn't be doing, namely collecting data across the cardiac cycle constantly, regardless where the heart is as a function of respiration or the cardiac contraction and relaxation. He just told me, just keep collecting data and worry about it later. So I found this rather interesting because I was always thinking the other way around. I let him do this. Unfortunately, this led to a whopping 12 gigabytes of data. Now you can imagine how much disk space I have to buy every year. But what you can do with this is, if you know something about where this was in the cardiac cycle, you can start puzzling together these different data segments which were acquired at the same time point. And because all these data were acquired radially, with the golden angle rotation, you can actually select a slice out of this totally arbitrarily where it is, how wide it is. You always have a homogeneous or the rather homogeneous K-space you can reconstruct, as you can see here. You can go and reconstruct images across the cardiac cycle, or if you want, you could also go to mid-diastole, reconstruct a larger segment to visualize the coronary arteries in a static way. Now, I would like to remind you that these data were motion corrected, so different motion states were actually corrected relative to each other in K-space. Now this young man here had the brilliant idea to look at this superior-inferior projection in these radial acquisitions, and then you get this blue wiggly signal out of it, which doesn't tell you really much, but if you Fourier transform it, you can see two distinct peaks, one being the cardiac contraction and relaxation, and one respiration. You can filter it out, you can back transform it, inverse Fourier transform it, and get the two beautiful signals out of this, one being the respiration and one being the cardiac cycle. And remember, these data are taken out of the K-space, which is acquired from for imaging. No EKG or no navigator is needed. Okay, if you then use that and dilute your data accordingly, remember, this is a golden angle 3D radial acquisition, and now you can start binning this according to different respiratory positions. So for instance, the green one being end expiration, and the red one being inspiration. So you just diluted the data. And of course, you can do a second thing. You can even more dilute these data in temporal direction to get different motion states of the heart. Now, of course, this is so heavily undersampled, these individual case spaces as they were, that you would get to images which look like this. So the whole exercise is basically for naught, right? Wrong. Because there is compressed sensing where you can exploit respiratory and cardiac correlations. You can plug this into such a reconstruction, and out come these images, just by using the intrinsic correlation you have between different respiratory states and between different cardiac states. Now, putting this to the test in patients, you can do this with different spatial resolutions, as you can see here on your right, 1.1 millimeters, 1.4 millimeters, and 2 millimeters in actually clinically acceptable scanning times, where during a free-running acquisition, you have everything in there. You have every cardiac contractile state in there, and if you're really interested in respiratory motion, you can also reconstruct that. So everything is in this one single scan, and if you compare this to a multi-slice 2D acquisition, actually the time you spend with this is quite favorable. I'm just not talking about reconstruction time, which is kind of prohibitive right now, but anyways. So we then also gave this technology to our friends at the Children's Hospital of Philadelphia, where they give Ferumoxytol to pediatric patients, and just out of the box, one click, these images came out, beautiful images in these pediatric patients without EKG triggering, without navigators, just Ferumoxytol. We also, in collaboration with Michael Markle and Liliana Ma is actually giving a presentation about this at this SMRA. We extended this to flow imaging again. I don't know how many dimensions these are, probably 5. But again, you do this during free breathing, no breath hold, no navigator anymore. And you can use this compressed sensing approach to then generate these flow images where you don't need an EKG or a navigator. These slides were given to me by Claudia Prieto, who do a similar thing. They subdivide their K-space into different respiratory levels. However, they do something much smarter than we do. They use respiratory motion fields to relate these images to one another, then to correct the images and to generate these images of the coronary arteries. Now, I'm always a little bit torn when I'm looking at these images. So on the one hand, I'm super happy that it is even possible to get such nice coronary images. Look at the comparison with CTA. It's even hard to tell which is which. Now, on the other side, I'm a bit jealous because having tinkered with this for more than 20 years, I was never able to get such nice looking coronary arteries as they are with this wonderful new technology. Debbie Ali has given me this slide here, and this is important because using MR, you can also look at the flow, and he actually took up the challenge to look into the flow in the coronary arteries. He plugs it into the Navier-Stokes equations, measures the pressure in these patients, excuse me, and comes up with a parameter which resembles FFR. And he did that, compared this to FFR, I think in 15 or 23 patients, and 24 as it were. And he looked at the correlation between FFR and the MR-derived equivalent, and he found a threshold here of 0.9, which would be a threshold which would be telling us that these patients who are above that threshold would not have to undergo an invasive test because their coronaries are sufficiently compliant, and there is probably no significant stenosis that warrants an intervention. Now, I was also given the task to talk a little bit about the thorax. Now, this whole idea of respiratory resolved reconstruction can, of course, be applied to the lungs. These are data which were collected by a PhD student of mine, Jean Delacoste, who did a 3D UTE acquisition where you can see different respiratory levels, and these are reconstructed using compressed sensing, and you can see different details showing up as you go through the respiratory cycle. And this is an example of a patient with bronchiectasis, where you can see very nicely on the MR how this hyperplasia here correlates with the CT, which is currently the gold standard. Now, these are pediatric patients often who have a longer and longer life expectancy. So therefore, it's hugely important to have tests without radiation. And I think with these MR technologies, if they advance a little bit further, maybe we could substitute 1 in 2 tests with MR rather than doing it with CT. And I think this would go a long way in radiation exposure for these vulnerable patients. Same thing here with air trapping, which you can identify on CT as much as you can on MR. Sorry to rush through this a little bit, but I think we are all hungry. And so I would like to conclude that contemporary techniques to account for respiratory and cardiac motion are, of course, breath holds, navigators, and the EKG. That will remain probably for quite a long time. But I'm also hoping that I was able to show you that there are more modern approaches, which include respiratory and cardiac motion resolved reconstruction, including compressed sensing, to account for these motion components, and they afford the advantage of improved time efficiency, improved ease of use, and reduced operator dependency. And with that, I would like to thank my team for jumping and for all those who were giving me slides for these presentations, and you for your attention.